In this session, we are going to study the concept of recursion. In recursion, it is possible to use the concept of recursion by using the stack data structure, and we are going to see how we can use this data structure for the concept of recursion. So before starting with recursion, let me first revise the different types of variables that we have seen already. So we have seen global, local, and static variables. Global and static variables are initialized to 0 automatically, implicitly, if you do not initialize them, and they can be accessed. Global variables can be accessed throughout the program. So if any one function makes a change in the global variable's value, then that change will be reflected throughout your program. Static variables are local to a function, but their lifetime or their existence is throughout the program. First time, if you call the function and if it includes a static variable in its definition part, then it will be initialized to 0 if you do not initialize. But if you have initialized to some other non-zero value, then it will be initialized to that particular value. And then second time, if you call that function, it will not initialize it again. The previous value of the first function call, that will be carried forward. For example, if initially the static variable value is 5, you call the function, you increment the value, it becomes 6. Then second time when you call the function, the value 6 will be considered. It will not be reinitialized to 5. Then similarly, we have local variables, but they are local or specified or restricted to a particular function only. So once you execute that function, you'll be able to use that local variable. And once you return back to the main function, then the function in which the local variable was, it has been deallocated memory. So that variable can be accessed only from that function. If you try to access that same variable from some other function, it is not possible. It will give you an error. So we know that there are 4 sections in the memory that is allocated to a program. That is heap, stack, data, global, static segment, and code segment. In the heap segment, we can allocate memory dynamically with the help of pointers, which we need to see. In stack area, the memory will be allocated to the functions and all the variables that are present in the function definition. For instance, here we can see that in the main, we have the values, the variables a and b. So main will be allocated some memory in this stack region. And whatever variables are used in main, they will be allocated memory a and b. Similarly, within the same stack, if you call a function f and it has a variable I in it, then that function f and the variable I will be allocated memory in the stack, right? So whichever function we call, if some variables are used in it or any other entities are there, they will be allocated memory in the stack for that particular function. Then we have data or global or static segment. This is used to store the values of the global or static variables, right? So that they can be accessed throughout the program. And the code segment will store the actual code or the instructions of your program. So now let us see that what happens when we call a function. Suppose you have a main function. Within that main, you have certain variables, say int a. Then within the main, you're calling a function f. And after that, you again have some statements. Okay. And this function f has been defined over here. And in this function also, you have a variable, say b. So in your stack, first time the main function is called. Okay, who will call the main function? The operating system calls it. Okay, now the main will be allocated memory in the stack. and the variable a which is in the main, that will also be allocated memory. Now next, when you want to execute this function call, that means control will jump from this call part to the actual definition part of the function. That time memory will be allocated on the stack so that this particular function can be executed. So the variables in that function say b, that will also be allocated memory. Now all the statements in the function get executed. Control should jump back to the main function at the calling. Okay, control will jump back at this position, and then the remaining statements will get allocated. When control jumps back to the main, whatever memory was allocated to the function f, that will get deleted. So this particular memory which was allocated is now erased. Then the remaining statements of the main will get executed, and once all the statements of main are executed, there will be a return of the control to the operating system. Okay, as we call functions, from the main we can call different functions, but who calls the main function? The operating system. So once all the statements in main are executed, where the control returns from the main, it will return to the operating system. So then the memory which was allocated to main also will get deleted or deallocated. So finally, by the end of your program, your stack will remain or become again empty. So this is how you can keep a track of which functions have been called and where I need to return with the help of stack data structure. This is the stack which helps to execute your program and the functions within your program. Now, this same function f can be called multiple times in the main. It is not necessary or compulsory. You can call it only once in the main. The same function can be called multiple times like this from the main function or any other function also. So the control will jump to this statement, then it will be executed, memory will be allocated. Once it returns back, this memory will be deallocated. Then second time again control will jump to the definition part because I'm calling the same function again, and then memory will be allocated again to that function. And once control jumps back to the main, again memory will be deallocated to that function. And now I'm in the main part. After all statements of main are executed, memory to the main will also get deallocated. So finally your stack is empty. And this was simple function call in which we are calling from the main. Okay, we can call one function from another function also, not necessarily only from the main. And this was the simple function definition and function calling. Now if we modify the calling, we can use the concept of recursion. Now first of all, why do we use recursion and what is recursion? We use recursion when we want to divide a given bigger problem into smaller sub problems. The given original problem is of huge size or it is very complex, then we can divide it into smaller parts, solve the smaller parts, combine their solution to get the solution of the bigger original problem. And in recursion, usually the nature or the type of the given bigger natural original problem is usually same, and the nature of the sub problems is also same. Okay, that is how we can implement recursion. The nature of the original problem and its sub problems can be same, and it becomes easier to solve the sub problems. And the exit condition when we should stop recursion, that is determined by the base case. Okay, we'll see what is base case, and we have to go in the reverse order, right? For example, suppose you have a function f. You have divided it into a part called f1. This f1, you have divided it into another part, smaller part called as f2. This f2 you have again divided into a smaller part, f3. Okay, so suppose f3 is the type of problem which can be easily solved, and you cannot divide f3 further into smaller parts, then f3 you can consider as your base case which you can solve easily and independently. Once you solve f3, you go back to f2. Okay, just a minute. Once you solve f3, you need to go back to the function who has called it, or you need to go back to its parent function, you can say. You'll go back to f2. Then you'll solve f2. You have found the solution. Now you can go back to f1. Then from f1 you can go back to f. So while decomposing, you go from top to bottom, you can say, and then you find the solution of the bottommost function, and then you keep going in the reverse order, and finally you'll reach the original given larger problem so that you can find its solution after combining the solution of its sub problems. I hope you have understood how we go about with recursion. It can be applied when we have the smaller sub programs, right? Now, before going to the different types of recursion, let us understand one example based on recursion. We have seen the program of factorial, right? So, in factorial, what we are doing, we can find the successive multiplication of the consecutive numbers after we decrement it by 1. For example, if we have a number 5, then how to find its factorial? You will multiply it with 5 minus 1, that is 4. Then you'll multiply it with 4 minus 1, that is 3. Then you'll multiply it with 3 minus 1, 2. Then you'll multiply it with 2 minus 1, 1. And then if you decrease 1 also, if you decrement it by 1, it becomes 0. And that is the time you need to stop. So you go to n, multiply it with n minus 1. That you'll multiply with n minus 2. Then you can multiply it with n minus 1 and so on. N minus 3, sorry, and so on. And once n becomes 0, once n becomes 0, you have to stop the factorial multiplication. So that is what we have seen already. Suppose n is greater than 0 initially, then in a variable res, initialize it to 1. Then what we do, res is equal to res into n. So we have multiplied n with 1, and then we decrement n. Then we'll multiply it with 4 and store it in res itself. Again we decrement and we multiply now 3. Again we decrement, we multiply 2. Again we decrement, we multiply 1. Okay, and then again we decrement, n becomes 0. So while condition is violated, n is not greater than 0, n has become 0. So we will terminate. So one more indication that how you can convert an iterative program into recursive program is wherever the iterations are there or wherever the looping statements are there, whatever code is written within the loop, that should be written into a function. And that function has to be called again and again. In iteration, what we were doing, we were executing the loop again and again. But in recursion, what we do, we call the same function again and again. Okay, we'll see the example now. See here, initially I have defined a function called as factorial and pass the n value. That means the parameter n will hold the number whose factorial I want to find. Suppose n is equal to 3. That means I'm finding the factorial of the number 3. Then what you will do? You will compare n with 0 initially. If n is 0, we have to stop. So that time return 1, suppose. Okay. But initially n is not 0. So what I'll do? I have to find out the value of n into factorial of n minus 1. Now see, the name of this function which I've called factorial and this function which I'm writing here in the return. In this return, what I'm writing the same function name. Here also I've written factorial. Okay, this is called as recursion. That means within the function, you're calling the same function. Within the definition part of the same function, there exists a call to the same function. But here what I've done, I've not passed the parameter as n. I've passed the parameter n minus 1. So what is happening? We can understand this concept by a recursion tree. Okay, let us draw the recursion tree. Any recursion problem or recursive algorithm can be solved with the help of recursion tree. So initially I'm calling the function of factorial on the value 3. Means I want to find the factorial of 3. Here n is equal to what? 3. Now first when I call the function, What I have to do? I have to check with n equal to 0. 3 equal to 0, false. That means my n is not equal to 0. So the else part will get executed. If else part is getting executed, I have to compute the value of n into factorial of n minus 1. That means once I call this function, I need to execute n, that is 3, into factorial of 3 minus 1, that is 2. Right? Now on the value 2, I have to call the same factorial function. So again, I will compare 2 with the value 0. I'm comparing n with 0. Is it same? No. That means else part gets executed. What is the else part? I have to compute 2 into factorial of 2 minus 1. That is 1. Now I have to call the same factorial function on this n value. Here the n value is what? 1. So what I have to do? I have to compare this 1 with 0. If condition is not satisfied, else is satisfied. That means I have to compute 1 into factorial of 1 minus 1, that is 0. Now this n value is what? N is equal to 0. Now 0 has to be compared with what? 0. If condition satisfied, I have to return 1. So whenever I have told you that whenever we return a value, we can say that the value of the function call is that particular value which is returned. For example, here if I am returning 1 from the function fact, then here I have written, right, fact of a. I have called the function here and I'm returning 1. So in place of this function call, the value 1 is replaced. And this value 1 will get stored in the variable result. Right? Whatever function we call, if it returns some value, that value comes in place of the function call. So indirectly we can say that the value of the function call is equal to the value returned by that function. I repeat, the value of the function call is the value returned by that function. Okay, this is how we can access the value which is returned by the function. Now I am returning 1. I am returning the value 1 because I've applied the factorial function to the parameter 0. If condition is satisfied, I have to return 1. So the value of this function call on the n value equal to 0, what is the value of this function call? The value of this function call is 1. Okay. So now what I have to perform? 1, this 1 into this 1. So 1 into 1 is 1. And that will come where now? This 1 will get returned to this function call. So now this 1 has come over here. Right? So the value of this function call f of 1 is 1. Now I have to perform 2 into 1. What is 2 into 1? It is 2. So this value 2 has to be returned to this function call. Above, we have to keep going above because I've told you reverse order we have to go, right? So here this is 2 now. Now I have to perform this 3 into this 2. 3 2s are 6. So 6 will get returned over here. So the function call on the value 3. What is the value of this function call? 6. And 6 is nothing but factorial of 3, right? 3 into 2 into 1 is 6. So using recursion, we have successfully found out the factorial of the parameter n. That is, here n is 3, so its factorial is 6. So this function call f of 3 has been done from the main, right? First time when we call the function, what I've done it? I've called it from the main function. Right? I've called this fact function from the main. And then multiple times I have to call it within the same function. So when I reach the topmost level, that is this particular level, when I reach this level, I have to return back to my main. Okay. All this time I was calling again and again the same function, but now I've reached the topmost level. I have to return back to the place from where the function was called for the first time. From where it was called for the first time? From the main function. So I've returned there and the value of the function call is 6. So I have found out the factorial. Okay. So each iterative algorithm or each iterative statements can be embedded or inserted into a function, and that function can be called again and again. This is nothing but recursion. Okay, I hope you have understood this. So any complex recursive problem can be solved with the help of such recursion tree. Another way to visualize this, I'll show you now. Okay, we have sort of formed a tree and kept on going deeper and deeper. Once we reach the base case, what is the base case here? When n is equal to 0, it is my base case. Base case means nothing but you can solve that case without recursion. For all the other cases, what you have done? For all the other cases, when n was not equal to 0, you have called the function again and again. When n was 3, you have called this function for 3 minus 1. When n was 2, you have called this function for 2 minus 1. But once n became 0, I did not call the function again. I simply returned 1. And this indicates my case of exiting the recursion function. Otherwise, you'll keep on calling the function again and again. How to exit from this recursion? By the base case. Base case is the subproblem which can be solved without calling the function within itself. Right? When the base case, that is when n was equal to 0, I have not called the function factorial again. I have simply returned 1. But for all the other cases, that is the general case or the recursive case, I have called the function factorial again and again for the different parameters. Right? I hope you have understood this. So only if there is a base case in your program, you will be able to exit from the recursion. Otherwise, you'll keep on calling the function within itself, and it may cause certain error, because if you don't exit from it, it will cause memory overflow. Okay, in some cases, you may not need a base case, and that we will see in future. But for now, remember that base case is the way to exit from the recursive calling. Okay. Let us see another way to visualize this. See, initially I called the function for the parameter n equal to 3. Once I called it for n equal to 3, what I did, first I checked 3, whether it is equal to 0 or not. 3 equal to 0, false. So the else part got executed. What happened in the else part? I did 3 into f of 2. Right? So from this, my control should jump to the definition part of the function with the parameter 2. Right? Now my control should jump to the same function, but with the parameter 2. Just a minute. So for the function with parameter 2, again I will check 2 equal to 0, false. So I have to do the else part execution. That means 2 into f of 2 minus 1, that is 1. So now control will jump to the definition part of the same function, but with a different parameter, which is 1 in this case. So again I'll check 1 with 0. Is the condition satisfied? No. So else part gets executed. What will happen now? I have to execute 1 into f of 0. So again the control will jump to the function, but with the parameter 0. Now what will happen? 0 equal to 0, condition satisfied. So if condition will executed, else condition will not get executed. If condition is getting executed, what I have to do? I have to simply return the value 1. Where this 1 will get returned? Yes, where this 1 will get returned? It will get returned to the previous function which had been called. So this 1 will come over here in this place. So the value of f of 0 function call is now 1. So 1 into 1, that is 1, will get returned back to this function call. Okay, so I'll get 1 over here. Then 2 into 1 is 2. So now control will jump back to this function call. So here it will come 2. So 3 into 2, 6. So 6 will jump back to the main. And I can print this 6. Okay, because from main I have called this first time. Okay, I hope you have understood the recursion tree and also this block kind of diagram to understand the recursion. Okay, just recollect what all I have taught till now. Yes, so now each successive recursive call should indicate that you're going closer to the base case. Okay, as soon as you call a recursive function, that means if you call the function within itself, you have to, it should be such that you're growing or you're approaching closer to the base case. Because if you're not going closer to the base case, it means that there is some error in your coding. Here what was happening, we were approaching to the base case. What is the base case? Base case is n equal to 0. And once we reach to the base case, we can simply go in the reverse order so that we come out of this recursion. Okay, so each time you call the function, ensure that you're approaching closer to the base case. Now, a case for which the answer is known and can be expressed without recursion is called base case. I have told you, right? Whenever base case came, when n was equal to 0, I did not call the function again. I simply returned 1 because I can solve the base case without calling the function again. Each recursive algorithm should have at least one base case. Okay, you can have multiple base cases for the input, but at least one you should have. And the other case is what? General case, general recursive case. In that case, what was happening? You had to call the function again. So general case is the case when you call the function again within itself, but base case is the case when you do not have to call the function within itself. Okay, keep this in mind. Now, what is the difference between recursion and iterations? In iteration, what we are doing? We are calling some looping statement and we are doing n into n minus 1 into n minus 2 and so on up to 1. Okay, for the number n, suppose n is equal to 5, you're finding the factorial of 5, then you must go up to, you have to keep on decrementing, and if n is equal to 0, it is 1. Okay, if n is not equal to 0, you have to keep on doing n into n minus 1 into n minus 2 and so on. But in recursion, what we are doing, if n is not equal to 0, we have to perform the multiplication of n into factorial of n minus 1. That means instead of multiplying with n minus 1, we are multiplying with factorial of n minus 1. That means we are calling the same function for the another parameter, that is parameter n minus 1. Okay, that means, see, we are doing successive multiplication, means the operation of multiplication is common. That means the original problem also has multiplication. Its sub-problems also deal with multiplication. That is why I said that original problem and its sub-problems are of the same nature. If this is the condition, then only recursion is successful. Okay, I hope you have understood difference between iteration and recursion. Now, which is better, iteration or recursion? That also we will discuss. In some programming language, recursion is compulsory. Okay, examples of such languages is Lisp. Lisp is a type of programming paradigm, okay, in which there are function oriented. It is function oriented, and there is Prolog also as another example. Okay, it is logic or rule based. Okay, and in such programming languages, okay, there are different programming languages other than C, C++, Java, Python, such as Lisp and Prolog, which follow the different programming paradigms, which we have already seen in the first lecture of this course. They have compulsory use of recursion. Okay. See, another way to visualize the factorial is what? Initially, if n is equal to 5, then you will you will jump to the function, you'll execute it, and n is not equal to 0, so you'll do 5 into factorial of 5 minus 1. Okay, then that means you're executing the same function for the parameter 4. So then 4 into factorial of 3, then 3 into factorial of 2, 2 into factorial of 1, 1 into factorial of 0. Factorial of 0 is what? 1. That is your base case when n is equal to 0. So you'll return 1. That means the value of this function call, the value of the function call for the parameter 0, the value of the function call factorial for the parameter 0 is equal to the value 1. That means 1 will come in place of this function call. Whenever we call the function for n equal to 0, it returns 1. So 1 I have written. Okay, all this time we were going this way. Now we have to go reverse. We have to keep on opening the bracket now. So 1 into 1 is 1. So I have to perform 2 into 1. That means this case and this case are same. Okay, reverse order. This is one part of the execution. This is the reverse order execution. Okay, so let me draw a separating line. All this was when you had the recursion, when you had to call the function again and again. Once the base case is reached, you have to go in the reverse order. Okay, that is the second part. So I have separated both the approaches. You have to keep on going deeper and deeper, and once you reach base case, you have to go outside or higher and higher. So once you achieve the base case, you have to keep on opening the bracket, sort of. So 1 into 1 is 1. Then next I have 2 into 1 is 2. Then 3 into 2 is 6. 6 into 4 is 24. And 24 into 5, 120. And this is your final factorial of 5. Right? So you can visualize recursion in different ways. One is the recursion tree. One is the block kind of diagram. And one is this brackets. So in recursion, you should take care of the size, how many times or how deep we are going to call the function, and determine the base case properly. The base case should be such that it's satisfies the program requirements. You can have more than one base case also. And the best case for factorial is n equal to 0 because factorial of 0 is 1. That is why we were returning 1. Okay. And determine the general case. That means what should be the parameter that you need to pass to the same function. Each time we are passing n minus 1. Okay. And the problem should be such that once you call it recursively, it should be expressed as a smaller version of itself. That means the nature of the given problem and its subproblem should be same. You should verify your algorithm before executing. Okay. It is a good practice to manually check whether everything is correct and then run it. Even if you don't check whether it is correct, it will shoot out an error, but it is always better to manually check it before running it. Now, we have seen that how the function is getting executed recursively. But what happens internally? How the computer can manage so many function calls, that too for the same function. Why I'm saying same function? Because you're calling the same function again and again within itself. So does the compiler get confused that which function should I is considered at the moment, where I should return, how I should return, should I stop now or should I keep on executing? All these problems are taken care of if we consider the memory organization. Right? How in structure padding and packing we have seen how it happens internally, that we have to see for recursion how it happens internally. So consider this case in which from a function b, this time not from main, from a function b I am calling a function a. A is a function. Okay, I have defined it above b. The name of a function can be a single character like ab also, not an issue. It should be a valid identifier. That is the only criteria. So you have to call the function a within b or from b, passing the parameter x. And this x is what? The x which has been passed to the function b. That means suppose from main I have to call the function b, and for that function I'm passing the parameter, suppose 5. So then the value of x will be 5. So control will jump from here to the definition part over here. Then z is equal to function call. So I have to jump from this to this definition part of the corresponding function. Then wherever parameter I passed, it is getting stored in w. I have to return w plus w, and then return back over here, and then do plus y, and then whatever will be stored in z, I have to return, and where I will return back to my main function, right? Whenever there is a return or whenever the statements of function are completely executed, I have to return back to the place from which it was called. I hope you understand this. So whenever there is a normal function call, or whether the function is called recursively, that is within itself, how the compiler or the system can take care of where I have to return, that is handled by the memory organization part, which we are going to see at the moment. Whenever you jump from one place to another place, that is the control jumps from this a part, this a function call, the control will jump to definition part. Okay, whenever this jump occurs of the control, all the execution within the function b will be suspended, or it will be at standby condition. It will not be executed at the moment. Why? Because control has jumped from the function call to the definition part. I repeat, whenever I come across a function call, control will jump to its corresponding definition. And that time, all the execution within that function b will be suspended, or it will be on the standby, or it will be on hold. And once my control returns back from the called function, when my control will return back, when all the statements of the function are executed, whenever all the statements of the function a are executed, that time my control will return back. Where it will return? To this calling part. And then I will do plus y. That means after the control returns to the calling, whenever the control returns back to the function call, right? This a of x is the function call. Whenever control returns back there, I can continue the execution within the function b. I can continue the execution within the function b after the control returns from a to b. And that time I can do plus y. That means the further execution can be performed. Right? Similarly, from here I will return to my main, and then the remaining part of the main can be executed. So whenever the control transfers to some other location or to some other function, the execution within the previous function will be held, or it will be on standby, or it will be suspended. I hope you have understood. So whenever the control will jump to some other location in memory, right? Each function is allocated memory. Each function will start at a particular location in memory. That means control is getting transferred to some other location. Before it jumps to some other location, an activation record is created on the stack. This activation record stores certain information about the function. In this case, suppose I'm jumping from B to A, then an activation record of B will be pushed onto the stack. I repeat, now I'm jumping from this function call. That means I'm jumping from this function B. I'm jumping from B to the definition part of function A. I've jumped, but before jumping, an activation record of the function b will be pushed onto the stack. Activation record, okay? It is not the memory that is allocated to the function. It is the activation record of the function. Here what we were doing, we were allocating the memory whenever the function was being called. Right? Whenever f function was being called, it was allocated memory on the stack. Whenever the control returned back, the memory was deallocated. But here what I'm saying, an activation record will also be pushed onto the stack whenever, just before returning, just before jumping. Okay, just before jumping to function A, I have to push the activation record of function B. This activation record contains mainly two parts. That is the return address. That means where I have to return. After I jump to function A, I will execute all the statements and I will return back to the function B. But where I have to return? This will be taken care of the portion of the activation record which stores the return address. The return address, that means where I have to return after executing a particular function, that will be stored on the activation record of the previous function. That means the activation record of B will have an activation record. The function B has an activation record, and that will be pushed onto the stack. Okay, where the function should return after executing, where the control should return after executing A, that will be stored. in the activation record. And the suspended status, that means where I have stopped within B, where I have stopped within the function call of B, where I have stopped within the function B, I have stopped over here, right? Here I have jumped, the control has jumped to some other function. That means here I have stopped the execution of function B. Okay, this suspended status will be stored, and where I have to return, that will be stored. And once you return back to the function B, the activation record will be popped off the stack. That means it will be removed from the stack. Okay, this happens in normal functions also, and in the recursive function calls also. So what is an activation record? It is basically a type of data structure which uses stack. And at the runtime, that is when you're executing, actually when you're running the program, these activation records will be created for the function. And it is used to maintain the particular information, that where I have to return, how much is suspended, and all that. So here I'm executing a function. There are some statements in the function. And then there is a return. So the activation record of F will be created. Just a minute. Okay, so the activation record of F is created. It stores in the stack area, there will be some memory allocated to X and Y variables, and whatever is the return value. Then if you study microprocessor, there is one program counter, that related information, whatever input output, if you are using file handling, that particular information. And for every activation record, there is a control link and an access link part, or access link and control link field. Link is nothing but it indicates the pointer. Now how this is used? See, from main you're calling a function F, so control will jump over here wherever F is defined. From F you're calling a function G, so control will jump over here wherever G is defined. Whenever G is executed completely, you'll return back to whenever G is executed completely, you'll return back to its calling part and execute remaining portion of F, and then you'll return back to the main. Okay, so what happens? Initially the activation record of main is there. Okay, then memory will be allocated to F function whenever it is called, so that you can execute it. So activation record of F will also be created. Then you're calling G, so activation record of G is also created. Once all the statements of G are executed, of G function, then you have to return back to F function. So that time it will be deleted or popped from the stack, whatever memory was allocated. How it knows where I have to return? Because the control link of G, the control link of the activation record of G function, stores a pointer to where it has to return. And this pointer is to a location within the F function. That means somewhere within F, I have to return. Where somewhere, I have to return at the call. Okay. The control link of the G function activation record, the control link of the activation record of G function stores the address to which it has to return within the F function. Similarly, you'll execute the remaining statements of F. Then the control link of the activation record of F function stores the address to which it has to return within the main function. Okay, so that will also be deleted. Activation record of F will also be popped from the stack. Then I'll return to main. After executing all the statements of main, I have to return to the function or the system which has called the main. Who calls the main? The operating system. So I have to return to the operating system. So the control link of the main function, stores the address or a pointer to the location within the operating system to which it has to return. Okay, because whatever you want to execute, the operating system will give you the permission. Suppose you want to execute a program, the operating system will call the main of that program. It will call the main function of that program. Okay, I hope you understood how we know where we have to return within the function using the control link of the activation record of that particular function. Now there are different types of recursion such as simple, sequential and nested. What is simple recursion? When you're calling the function only once within itself. Here what you're doing, you're calling this function f within itself only once. It is simple recursion. What is sequential recursion? You're calling the same function twice and maybe you're performing certain operation between them like multiplication. And that whatever you multiplied will be stored in a variable x, suppose. Right, you're calling the function multiple times, one after the other. Means this function call and this second time function call are at the same level, right? So they will be executed and whatever value is returned by them, it will be multiplied and stored in a variable x. So these two function calls are one after the other in a sequence. Okay, sequential recursion. Another thing is recursive. Another form of recursion is nested recursive function call, in which you're calling the function again and again, but you're passing the parameter as a function call. For example, you want to call the function f. First time you call the function, within the function f, you're calling again the function f. So you're writing f, and as a parameter, what you'll pass? Again a function call, which calls the same function f. Okay? I hope you have understood. We are calling the same function, but passing it as a parameter. That means if you're calling a function f, you're passing certain parameter to it. In this case, the parameter is a function call. So whatever value is returned by this function, inner function, whatever value is returned by the inner function will be replaced at this function call. Suppose the value returned by the inner function is 1. Then in place of the function call, what will come? The value 1. And 1 will act as the parameter. So you're passing the function call as a parameter. To this inner function also you may pass certain value. And this inner function is returning the value 1. That will come in place of this function. And 1 will act as a parameter to the outer function. Right? Give this a thought. I am sure you'll understand it. Nested function calls. Now, within the function, you're calling the same function as a parameter. You're calling the function by passing a parameter, which is a function call, to the same function. Then you may perform certain multiplication, and then you're calling the same function again. Means what? The parameter passed to this outer function is nothing but the multiplication between two function calls. So this particular function will return certain value. This function will return certain value. You're multiplying them and passing the product of this multiplication as a parameter to the outermost function, right? Similarly, here another example, f of 3 is called. Within f of 3, you're calling the same function for the parameter 2. Within this, you're calling a function, same function for the parameter 1. So initially, f of 3 activation record is there, then f of 2 activation record is there, and then f of 1 activation record is there. So the control link of function 1 stores the address to which it should return within this function. So after the execution of the function for the parameter 1, the control link part will help you to return to this function call for the parameter 2. Then the control link of the function call for the parameter 2 will return to the function call with the parameter 3, and then finally to the main by the control link of function call for parameter 3. So control link of a particular function helps you to return to the particular location within the previous function. This mechanism is same for the normal function calling, that is where the function names are different, or if the functions names are same, it is recursion. That time also control link and activation record is used. So I hope you understood this much, that how, what is recursion, some basic differences between normal function call and recursion or recursive function call, then how we can identify or solve the recursive problems using recursion tree, either block diagram or opening the brackets, right? And how the memory management is done so that we know where we have to return using the activation record and the its control link. Okay, the remaining part we'll cover in some other video, in the next video. Thank you.